Welcome to the deep dive. Today, we're setting out on, well, kind of an adventure, really. We're going to try and unravel a mystery that's happening all around us, all the time. Something so common we maybe don't even think about it much.
What's that?
The wind. You know, that invisible push you feel. It rustles the leaves, fills up sails on boats, cools you down on a hot day.
Right. We feel it constantly.
Exactly. It shapes our world, sometimes gently, sometimes, well, not so gently. But have you ever really stopped and wondered what actually makes the air move?
It's a great question. It feels like something just decides to blow.
It can feel like that, yeah. Almost like an unseen hand. So today we're pulling back the curtain, and our guide for this deep dive actually comes from a really neat source, a Curious Kids guide, which is brilliant because it breaks down some pretty big ideas really simply.
Oh, that's perfect.
Yeah. Get ready to explore the, I guess, surprisingly elegant science behind why the wind blows.
And that really is our mission today, isn't it? To take what seems like this super complex atmospheric thing and break it down.
Into understandable bits.
Exactly. Into concepts that hopefully shine a light on the beautiful physics going on underneath it all.
Yeah.
We want to show that wind isn't really mysterious. It's more like a continuous dance happening in the atmosphere.
A dance. I like that.
Yeah, and it's all driven by one main energy source. When you look at the steps, it's actually pretty logical.
Okay.
And understanding it, I think, gives you this amazing appreciation for our dynamic planet. We'll sort of unpack the basic mechanics of how air gets moving and why that movement is so important.
All right, let's dive in then. Where do we start? With the main character, I suppose.
You mean the sun?
Exactly, the sun. It's this huge, constant heater for our whole planet, right? Just bathing us in energy all the time.
Absolutely. It warms everything: mountains, oceans, forests, deserts, everything.
That steady stream of energy really sets the stage for, well, pretty much all the weather that follows.
It's the foundation.
But here's where it gets really interesting, and maybe this is the core of it. Even though the sun's so powerful, what do you think happens because it doesn't heat the Earth evenly?
Oh, right.
Like, imagine some parts get way hotter than others right next to cooler spots. What kind of chain reaction would that uneven heating start?
You've absolutely hit the nail on the head there. That question gets right to the heart of it. That is the key to understanding wind.
Really? Just that, uneven heating?
Fundamentally, yes. The sun, huge as it is, just does not heat every part of Earth the same amount.
Yeah.
And that difference, that unevenness, it's not a minor detail.
Okay.
It's the essential driver for pretty much all the big air movements in our atmosphere, including the wind we feel every day.
So why isn't it even, I mean, the sun's just shining, right?
Well, think about the shape of the Earth first. It's a sphere, a ball.
Right.
So when sunlight hits the equator, it's coming in almost straight on. Bam! Concentrated energy in a smaller area. That makes the equator regions generally much warmer.
Okay, makes sense. More direct sunlight.
Exactly.
Yeah.
But as you move towards the North or South Pole, the Earth curves away. The sunlight hits at more of an angle, a slant.
Ah, so the same amount of sunlight gets spread out.
Precisely. Spread over a much bigger area. So the energy is diluted, weaker per square meter, you could say. That means colder temperatures near the poles.
Gotcha. Equator hot, poles cold. Big difference.
Huge difference. And that large-scale temperature contrast is what drives the massive global wind patterns, the big atmospheric circulation. But this uneven heating also happens on much smaller scales all the time, creating the local winds we notice.
Okay, like what kind of smaller scales?
Well, the classic example, something you've probably felt yourself, is the difference between land and water.
Oh yeah, definitely. Like at the beach.
Perfect example. Think about walking on the sand on a really sunny day. Hot, right? Sometimes burns your feet.
Totally. You do that little dance trying to get to the water.
Exactly. But then you step into the ocean. What happens?
Ah, relief. It's way cooler, instantly.
Way cooler. And that's not just random. It's because land and water handle heat very differently. It comes down to something called specific heat capacity.
Specific heat. Okay, sounds technical.
It does, but the idea is simple. Land, especially sand or dry soil, has a low specific heat capacity. Basically, it takes very little energy to make its temperature go up.
So it heats up fast.
Super fast, like 5 to 10 times faster than the same amount of water, given the same sunlight. Think
Yeah.
of land as a quick charge battery for heat. It sucks up the sun's energy really quickly, gets hot, but it also loses that heat just as quickly when the sun goes down or a cloud passes over. Quick to heat, quick to cool.
Okay, so land is like a sprinter with heat.
Good analogy. Now water.
Bro.
Water has a much higher specific heat capacity. It's like a huge heat sponge or maybe a marathon runner.
Takes more energy to get it
A
going.
lot more energy to raise its temperature even 1 degree. Partly it's the water molecules themselves, how they're bonded. Plus, water can mix.
Oh, right. Currents and stuff.
Yeah, currents, waves. The heat gets distributed down deep, spread through a huge volume of water. Land just heats the surface layer intensely.
So the ocean takes ages to warm up.
Exactly. But the flip side is, it also takes ages to cool down. Oceans act like massive temperature stabilizers for the planet, especially near coasts.
Right. Places near the ocean usually don't get as extremely hot or cold.
Yeah, that's why. So on a sunny day, you've got the land getting really hot really fast right next to the ocean, which is still relatively cool. Same sun, totally different temperatures.
Uneven heating right there.
Textbook example.
Yeah.
But it's not just land versus water. Think about different types of land surfaces.
Right what?
Ever walked barefoot on black asphalt on a summer afternoon?
Ouch. Yes. Unbelievably hot.
Because that dark surface just absorbs almost all the sunlight hitting it, turns it straight into heat.
Okay.
Now, step off the asphalt onto some green grass nearby. What's the difference?
Way cooler. So much better.
Right. Grass feels cooler, partly because plants use some sun energy for photosynthesis, but they also do this thing called evapotranspiration.
Evappo.
Evapotranspiration.
Mm-hmm.
Basically, plants release water vapor, like they're sweating, and just like sweating cools you down, this cools the air around the plants.
Wow. Okay. Plants are like little air conditioners.
In a way, yeah. And then think about light-colored surfaces, snow, ice, even light-colored buildings. What do they do with sunlight?
Reflect it. Like wearing a white shirt instead of black.
Exactly. They bounce a lot of the sun's energy back into space, so they don't absorb as much heat, they don't warm up as much.
So dark surfaces get hot, light surfaces stay cooler, plants cool things down.
And even cities. All the concrete and asphalt makes cities absorb and hold on to heat much more than the countryside. That's the urban heat island effect you hear about.
Right. Cities feel hotter.
They often are. So all these differences, land versus water, dark versus light, city versus country, they create this patchwork quilt of temperatures across the Earth's surface.
And this patchwork, this is setting the stage for the wind.
It's setting the stage for a truly spectacular natural show. It's the starting point for that atmospheric dance.
Okay, that makes total sense. The sun doesn't heat things evenly, creating hot spots and cool spots all over the place. So we've got the temperature differences. What happens to the air itself sitting above these different spots?
Right, that's the next logical step.
Mm.
What does the air do when it gets heated? Let's go back to that hot patch of land,
Mm.
maybe the beach sand or the asphalt.
Okay.
The air directly above it absorbs that heat from the surface. And when air molecules get heated, they get energized.
Energized how?
They gain kinetic energy.
Mhm.
Our source uses a great analogy. Think of the air molecules as tiny invisible dancers.
Okay, air dancers. I like it.
When they get heated, these dancers get a huge energy boost. They start moving around much faster, bouncing off each other, getting really lively.
Like a dance party heating up?
Exactly. And when dancers are moving wildly, what do they need?
More space.
More space. They spread out. They push each other further apart because they're moving so fast.
Okay, so the heated air molecules spread out. What does that mean for the air?
It means the air becomes less dense. Think about it. You have the same amount of stuff, the same number of air molecules, but now they're taking up a larger volume, more space.
Ah, so there's less stuff packed into any given spot.
Precisely. Less mass per unit volume. The air becomes lighter, or more accurately, less dense.
Okay, lighter air. And what do lighter things tend to do?
They float. They rise. Because this warm, expanded, less dense air is now lighter than the cooler, denser air surrounding it, it starts to lift.
Up
Up into the sky. It's buoyant.
like a hot air balloon.
Exactly like a hot air balloon. That's the perfect analogy. Why does a hot air balloon float?
Because they heat the air inside it, right, with those burners.
Exactly. They heat the air inside the big fabric envelope, making it much less dense, much lighter than the regular air outside.
Yeah.
And because it's lighter,
It rises. Buoyancy.
that's the principle. Lighter fluids, or gases, always rise through heavier ones. It's a fundamental law of physics, and it's happening constantly above hot ground.
Wow. Okay, so this rising warm air isn't just floating away, is it? Does it do anything else?
Oh, absolutely. First, as it rises, it creates an updraft, a column of rising air.
Updrafts, like birds use.
Precisely.
Hmm.
Eagles, hawks, even glider pilots are masters at finding and using these thermals, these updrafts, to soar upwards without flapping, saving loads of energy.
Cool.
And there's more. If that rising air has moisture in it, Water vapor.
Yeah.
As it goes higher, the surrounding air gets cooler and the pressure gets lower. The rising air expands and cools down itself. That's called adiabatic cooling.
Okay, it cools as it rises and expands.
Right. And as it cools, the water vapor can't stay as a gas anymore. It condenses.
Into
Tiny little water droplets or ice crystals. And what do lots of tiny water droplets or ice crystals make?
clouds.
Clouds. So the very act of warm air rising is directly linked to making clouds. And if enough moisture condenses, those droplets get bigger and
Rain. Or snow.
exactly. Precipitation. It
Yeah.
connects heating on the ground to weather way up high.
Mhm.
How fast it rises also depends on how stable the atmosphere is, but that's maybe a detail for another time.
Fascinating connection, though. Okay, back to the ground level. If all this warm air is rising, lifting off the ground,
Yes.
what kind of space does it leave behind down there? On our Earth's dance floor?
Excellent question.
Oh,
It leaves behind, well, fewer dancers, right? Fewer air molecules pressing down on the surface.
so it's less crowded down there.
Less crowded and therefore less weight pressing down. This creates an area of lower atmospheric pressure.
Lower pressure. Because it's literally less air weighing down on that spot.
That's exactly it. Atmospheric pressure is just the weight of the column of air above you. If some of that air floats away upwards, the weight decreases, lower pressure.
Like that empty spot on the dance floor analogy. If people float up, the spot they leave is emptier. Less pressure from feet on the floor.
Perfect. And that low pressure area, that empty spot, it's not just going to sit there, is it? Nature doesn't really like empty spaces or imbalances.
It feels like something has to happen next.
Something definitely has to happen.
Yeah.
That low pressure area is like a vacuum cleaner almost. It's an invitation.
An invitation for what?
They're the air from the surrounding cooler areas to come on over.
Ah, the plot thickens. So this low pressure spot is like a vacuum. But nature hates a vacuum, right? So how does the atmosphere fill it? What rushes in?
This is it. This is the moment wind is born. While the air over the hot spot is rising, think about the air over the cooler areas nearby. Maybe over that ocean or in the shade of a forest.
Okay, the cooler spots. What are those air dancers doing?
They're much calmer. They have less energy because they're cooler, so they're moving slower and they're staying closer together. More like a slow dance, maybe? Packed in a bit tighter.
Okay, slower, closer together. What does that mean for density?
It means that cooler air is more dense, more tightly packed, more air molecules crammed into the same amount of space.
So cooler air is heavier, denser.
Heavier and denser. It's the opposite of the warm air. More stuff in the same volume means higher density.
Got it. Warm air equals light and rises. Cool air exhales heavy and stays put.
Well, it would stay put except for that low pressure area nearby. Because this cool, dense air has more molecules pressing down, it creates an area of higher atmospheric pressure.
Okay, so hot spots have low pressure, cool spots have high pressure.
Exactly. And now you have a difference, a pressure gradient, scientists call it. High pressure here, low pressure over there.
Like a hill, but with air pressure. High point and low point.
That's a great way to think about it. A pressure hill.
Mm-hmm.
And what does stuff naturally do on a hill?
Rolls downhill, from high to low.
Precisely. Water flows downhill, air flows down the pressure hill. It always moves from an area of high pressure towards an area of low pressure. Nature is always trying to balance things out to level that pressure hill.
So the cool, heavy, high-pressure air sees that inviting low-pressure empty spot.
And it doesn't just drift over. It rushes in. Because it's denser, heavier, it flows down that pressure gradient to fill the void left by the rising warm air.
It rushes in.
Think about popping a balloon. The air inside is under higher pressure. When you make a hole, PA, it rushes out fast to equalize with the lower pressure outside.
Right, it doesn't just seep out slowly.
Or think of opening the doors on a crowded train or bus. People near the door in the less crowded station tend to move quickly into the emptier space inside, right?
Yeah, they fill the space.
That movement, that rush of cooler, denser, high-pressure air moving towards the warmer, low-pressure area that is wind.
Wow. So wind is literally just air rushing from a high-pressure spot to a low-pressure spot.
That's the fundamental definition.
Yeah.
It's air in motion, driven by differences in pressure, which are themselves caused by differences in temperature.
It seems so. Logical now.
It is. And this pressure gradient force, this push from high to low, is the engine behind all air movement. From the tiniest puff of air to a giant hurricane, the bigger the pressure difference,
The harder it pushes.
the harder it pushes, and the faster the air rushes to try and balance things out.
Okay, that leads perfectly to my next thought. We feel gentle breezes, but also really strong, powerful winds. If it's all just air moving from high to low pressure, why the huge difference in strength? What makes one wane a whisper and another a roar?
Excellent, critical question. And the answer ties directly back to those temperature differences we started with.
Okay, how?
It's actually beautifully simple at its core.
Yeah?
The bigger the difference in temperature between the hot spot and the cool spot,
Yeah?
the bigger the difference in pressure between them. And the bigger the pressure difference, the faster the air rushes in to fill that low pressure void.
So bigger temperature difference equals stronger wind.
Exactly. It's a direct relationship. More contrast in temperature means a steeper pressure hill, a stronger pressure gradient force.
Ah, the pressure gradient again, like comparing a gentle slope to a steep cliff.
Perfect analogy.
Yeah.
A small temperature difference creates a gentle pressure slope. The air moves slowly down if that's your light breeze, barely enough to rustle leaves.
Okay.
But a big temperature difference maybe between land that got super hot and an ocean that's still cool, or especially when a really cold air mass slams into warm air, like with a cold front.
Yeah, those can bring storms.
Right.
Yeah.
That creates a very steep pressure gradient, a steep pressure cliff. The atmosphere wants to fix that big imbalance fast, so the air rushes down that steep gradient with much more force.
It accelerates more.
Much more. That faster rush means the air molecules have much more kinetic energy, the energy of motion.
Kinetic energy.
More speed equals more energy. And that higher kinetic energy is what we feel is strong wind. It's the physical force of that fast-moving air pushing against us, against trees, against buildings.
So a stronger push from the pressure difference leads to faster air, which means more energy, which we feel is stronger wind.
You've got it.
Ah,
Think about that gentle sea breeze on a nice day. Land's a bit warmer, sea's a bit cooler. Small difference, gentle breeze.
right. Feels nice.
Now picture a really blustery day, maybe before a thunderstorm.
Mm-hmm.
Often that's because a much colder air mass is moving in, creating a huge temperature contrast with the warm air it's replacing. Big temperature difference, steep pressure gradient,
Whoosh, strong winds.
strong gusty winds. Or think about blowing out a candle. A gentle puff might not do it. You need a stronger puff, right?
Yeah, a faster burst of air.
That faster burst comes from creating a bigger pressure difference between your lungs and the outside air. Same principle, different scale. So next time you feel a really strong wind whipping around.
I should think, wow, there must be a really big temperature difference somewhere nearby.
Exactly. The wind strength is telling you how hard the atmosphere is working to balance out a significant temperature and therefore pressure imbalance.
But is it just the pressure gradient? Are there other things affecting the wind's speed and direction?
Good point. It's not quite that simple, especially on a larger scale. The pressure gradient force is the primary driver, the engine making the air want to move, but other forces modify its journey.
Like what?
The biggest one, especially for large weather systems, is the Coriolis effect.
Coriolis sounds familiar. Something to do with the Earth spinning.
Precisely. Because the Earth rotates underneath the moving air, the air appears to get deflected from its straight path from high to low pressure.
Appears to.
Yeah, it's not a real force pushing it sideways, but an effect of being on a rotating reference frame. In the northern hemisphere, moving air gets deflected to the right. In the southern hemisphere, to the left.
Okay. So the wind doesn't blow straight from high to low.
Not over long distances, no. The Coriolis effect makes it curve. The stronger the wind, the stronger the deflection. That's why winds spiral around high and low pressure centers on weather maps instead of just flowing directly across.
Ah, that makes sense why weather maps look like swirls.
Exactly. It changes the wind's direction significantly, but not really its speed.
Okay, what else?
Then there's friction, especially near the ground.
Friction, like air rubbing against things.
Yeah, rubbing against the ground. Trees, buildings, mountains, even the surface of the ocean waves. This friction acts like a brake.
It slows the wind down.
It slows the wind down near the surface, and by slowing it down, it also reduces the Coriolis effect's impact. So near the ground, the wind ends up blowing at an angle across the lines of equal pressure, isobars, sort of a compromise between the pressure gradient pushing it, Coriolis deflecting it, and friction slowing it.
So that's why it's often windier higher up, like on hills or tall buildings.
Absolutely. Higher up, there's much less friction, so the wind can blow faster and gets closer to being parallel to the isobars, mainly balanced between pressure gradient and Coriolis. We call that the geostrophic wind.
Geostrophic, got it. So the wind we actually feel is a mix of the push from pressure, the turn from Coriolis, and the drag from friction.
It's a constant balancing act between those forces.
Do we have ways to measure wind strength easily?
We do. Meteorologists often use the Beaufort scale. It relates wind speed to things you can actually see.
Oh, like leaves rustle or trees sway.
Exactly. Beaufort 2 is a light breeze, maybe 611 kilometers per hour, just rustling leaves. Beaufort 5 is a fresh breeze, 2938 kilometer air, small trees sway.
Oh, okay.
But then you get up to Beaufort 9, a strong gale, that's 7588 kilometers, strong enough to damage buildings. And Beaufort 12 is hurricane force, over 118 kilometers, devastating.
Wow. Huge range.
Huge range, all driven by the intensity of those pressure differences.
Mm.
And sometimes local geography creates unique strong winds too, like
Yeah.
Chinook winds in North America or foehn winds in the Alps. These happen when moist air goes up one side of a mountain, drops its rain or snow,
Yeah.
then comes down the other side. As it descends, it gets compressed by the higher pressure at lower altitudes, and that compression heats it up dramatically.
So you get warm, dry, fast winds coming down the mountain.
Very warm, very dry, often very strong winds that can melt snow incredibly fast. Or the Santa Ana winds in California, hot, dry winds blowing from the desert to the coast, which can unfortunately make wildfires much worse.
So even those specific named winds are just variations on the same theme. Pressure differences caused by temperature and sometimes shaped by mountains.
Fundamentally, yes.
Mhm.
Different ingredients, different terrain, but the basic physics of air moving from high to low pressure remains the same.
This is amazing, actually, when you put it all together like that. Okay, let me see if I can recap this whole journey in my head.
Go for it.
It starts with the sun heating the earth, but unevenly. Hot spots, cool spots.
Check.
Above the hot spots, the air gets warm, the air dancers spread out, the air becomes less dense, lighter,
Uh-huh.
and so it rises, like a hot air balloon, leaving behind an empty spot of low pressure.
Perfect.
Meanwhile, over the cool spots, the air is colder, denser, heavier, creating high pressure.
Right.
And this cool, heavy, high-pressure air rushes in to fill the low-pressure void left by the rising warm air.
The rush.
That rush is the wind. Its path gets bent by the Earth's spinning Coriolis and slowed down near the ground by friction.
Excellent summary.
And the bigger the initial temperature difference, the bigger the pressure difference, and the stronger that rush, the stronger the wind. Wow.
You absolutely nailed it.
It really does transform something we just feel into this visible process in your mind, this constant balancing act. That phrase from the source is sticking with me. Wind is simply air moving from a place where it's cool and crowded to a place where it was warm and empty.
It's such a clear and concise way to put it, isn't it? And it really captures the essence.
It does. It makes it feel less like a force acting on us and more like a process happening around us.
And that's the big takeaway, I think. Wind isn't just some random invisible thing. It's this magnificent, constant, natural force at work, a dynamic process driven by basic physics, temperature, density, pressure, and shaped by our planet's features and its rotation.
The earth breathing, you called it earlier?
In a way, yes. It's how the Earth redistributes heat energy across its surface, constantly trying to smooth out those temperature differences, always seeking that balance.
Now that I get the basics, I feel like I can look at the wind differently.
You absolutely can. Start observing. Think about why you often get that nice sea breeze at the beach during the day.
Okay, let's see. Land heats up faster than the sea.
Right.
So air rises over the land, low pressure there. Sea stays cooler, high pressure over the water.
Yes.
So the air moves from the high pressure sea to the low pressure land. Sea breeze.
Perfect.
Yeah.
You got it. And what happens at night?
Oh, land cools down faster than the sea, right?
Right. Quick to heat, quick to cool.
So at night, the land is cooler, high pressure. The sea is warmer, low pressure. The wind reverses, blows from land to sea, a land breeze.
Exactly. That diurnal cycle happens all the time in coastal areas.
So cool. What about cities? You mentioned they get hotter.
Right. The urban heat island.
Oh, yeah.
All that concrete and asphalt gets really hot, creating stronger updrafts over the city compared to the cooler surrounding countryside.
So that pulls air in from the countryside, making cities windier sometimes.
It often does, especially on warm afternoons. Creates its own little circulation. So knowing this stuff gives you a whole new layer of appreciation for, well, everything. The air, the weather, how interconnected our planet is.
It really does. It shows how even simple things aren't always so simple underneath.
And it scales up massively, too. These same principles, uneven heating, pressure differences, Coriolis, they drive the giant global wind belts.
Like the trade winds?
Exactly. The trade winds that sailors use for centuries, or the westerlies that affect weather across North America and Europe. even the jet
The
streams.
jet streams, those super fast winds high up.
Yeah, those narrow bands of incredibly strong wind miles up in the atmosphere. They're formed by big temperature contrasts and the Coriolis effect, and they steer weather systems around the globe and even affect how long your plane flight takes.
Wow. It's all connected, from a sea breeze to a jet stream.
All part of the same atmospheric engine. The amount of energy moving around in these wind patterns is just staggering.
Energy. Like usable energy.
Absolutely. Think about it. Humans have used wind power forever, sailing ships, windmills grinding grain,
Right, windmills.
and now massive wind turbines generating clean electricity. It's harnessing that same natural air movement driven by the sun's uneven heating. Wind also shapes landscapes, erodes rocks, builds sand dunes, spreads seeds. It's fundamental.
So feeling the wind is feeling the Earth's energy system in action.
It truly is, feeling the planet constantly working towards balance. So now that you've got this picture, this secret of the wind, what part of this whole amazing dance stands out most to you?
Gosh, I think it's that connection between something as huge as the sun and something as simple as feeling a breeze on your face. That direct line from uneven heating to rising air to rushing cool air. It makes the world feel both incredibly complex and beautifully logical at the same time. It just reinforces that idea that there's wonder everywhere, even in the air moving past us.
That's a wonderful way to put it.
Yeah. And that's really what we love doing here on the Deep Dive, isn't it? Just peeling back those layers, finding the stories and the science hidden in plain sight. We really hope this deep dive has sparked your curiosity. Maybe made you look at the wind a little differently.
Hopefully encouraged you to keep asking why about
Uh-huh.
the world around you.
Definitely.
So yeah, the next time you feel that cool breeze or maybe battle against a strong gust, remember those invisible dancers. Remember the sun's power, the pressure differences, the earth spinning.
And the air just trying to balance things out, rushing from the crowded places to the empty ones.
Exactly. And now that you understand how temperature and density differences and rotation drive the wind, here's a thought to take with you. What other big natural processes might be driven by similar hidden forces? Think about currents in the deep ocean, moving huge amounts of heat around.
Oh, interesting.
Or even, on a vastly different scale, the slow creep of tectonic plates deep inside the Earth, driven by heat and density differences in the mantle. Could the same fundamental ideas of heat, density, and movement be at play there too?
Wow, that opens up a whole new set of questions.
It does, doesn't it? The principles are often universal. Keep that curiosity going. Our world, our universe is just full of these elegant, interconnected systems waiting to be understood.